Hello students, so in this lecture we shall be discussing about Fermi level shifts that are occurring between when we are doing a contact between a metal and a molecule, as we have seen in our previous classes. So there are some Fermi level shifts. Now if EF0 is the Fermi energy of the neutral molecule, that means when there is no such type of contacts, and then we call the Fermi energy as EF0, and after the contact has been made, we call that energy to be EF. Now, what is the relationship between EF0 and EF is expressed in this equation. EF is equal to delta N, that is the charge transfer, divided by delta Q square by electrostatic capacitance into again the charge transfer plus the EF0, that means this. And we can draw an equivalent circuit where this part is your metal and this part is your molecule, and they are joined by resistance R, and this is where is the quantum capacitance, and this is electrostatic capacitance. That is an equivalent circuit. Signifying the contact. Now, you can also express the Fermi energy in terms of this quantum conductance. That is, EF is equal to Q square by quantum conductance into delta N plus Q square by electronic conductance delta N plus EF0. Now, the changes in energy level alignment when a charge is transferred from metal to molecule, that means when there is a charge transfer metal to molecule, there will be changes in the alignment of the Fermi levels. Like if this is the metal and this is the contact, it has got a work function. This phi is to think about the work function of the molecule. Now, when we are establishing a contact, there are HOMO and LUMO gaps. The difference between the LUMO to the vacuum energy is the electron affinity, and from the HOMO to the ionization potential, and with charge transfer there is a slight change in the energy level of the vacuum energy, and so this change in the vacuum energy is Q square delta N by CES. That means we are talking about this quantity here, and also the same amount of change will take place here, and also there is also previously defined EF0. So all these things will add up to your Fermi level of the electron, Fermi level of the contact, metal and molecule contact. Now, the charge in the molecule is actually, it means when we are applying a voltage across the capacitor and changing the potential of the molecule. So this is what is meant by charging or charge transfer. So there are vacuum level shifts at the molecular location, shifting all the molecular states along with it. Now, in addition, some previously empty states. So both of these will affect the Fermi level of the molecule. Now, if we consider isolated point contacts, now for a very small molecule, like for a single molecule, it is sometimes convenient to find out this electrostatic capacitance by assuming the conductor is a sphere of radius r. So we assume that from Gauss's law, the potential is given by Q by 4 pi epsilon r, where epsilon is a dielectric constant. We are assuming the distance at which the potential is much larger than the radius of the sphere. And if we take the potential at infinity to be 0, then the potential of the sphere is Q by epsilon 4 by epsilon r, and the electrostatic capacitance is Q by V, which is 4 by epsilon r. So the important thing is that electrostatic capacitance scales with the size of the conductor. So there is the charging energy of this small conduction will be very large. So this is the electrostatic capacitance for a radius of 1 nanometer, for a molecule of radius of 1 nanometer. The electrostatic capacitance comes out to be minus 19 farads, and the charging energy comes out to be 1.0 electron volt per charge. Now, if we assume that we take a conductor which is polarized between the source and the drain, and the source and the drain can be modeled as parallel plate capacitors having the following capacitance. A is the area of the parallel plates, and is the distance between the two plates. And there is a uniform electric field between the source and drain, and then this uniform electric field will only be valid if the area is much larger than the distance. That means we have these two parallel plates, these areas, so that the distance between them to D is much smaller. So for the source and electrode separated by a distance L, and the source and the drain at a distance Z from the source are, this is the capacitance at the source, and this capacitance at the drain. And the potential varies linearly for the uniform electric field, so it's minus QVDS 1 by CAZ divided by 1 by the source capacitance plus 1 by the drain capacitance 1 by the source capacitance, so that is equal to 1 minus Q squared VDS by L. And the capacitance of an oscillator zero-dimensional conductor is calculated by assuming that the potential infinity is 0. Infinity is 0, so this is the source and the drain. So there is flow of electrons, flow of charges from the drain to the source, and this is how the potential varies with the distance. So we assume that uniform electric field between the source and the drain, it leads to linearly varying potential between the source and the drain.